Today we are going to talk more about elementary stats. So our first problem is a basketball player makes 80% of her free throws. Suppose she takes 60 shots. Identify the parameters of the binomial setting NP 1 minus P and explain what each represents. So we know that N equals 60 because she takes 60 shots. So we know this is the number of trials, three throw attempts. And we know that P is 0.80. This is the probability of success on each trial, making a free throw. And 1 minus P, the probability, is equal to 0.20. This is the probability of failure, missing a free throw. So these are going to be our parameters. Question number 2 of problem 1, mean and the standard deviation of successful shots. So explain what the numbers mean. So to calculate mean, we're going to do N times P equals 60 times that probability, which is 0.80 equals 48. That will be our mean. And then the standard deviation is going to be the square root of N times P times 1 minus P, which is this equation right here. And then once we simplify it, we're going to get 3.10. So for the explanation, on average, the player is expected to make 48 successful shots out of 60. In other words, the number of successful shots typically varies about 3.10 shots from the mean. Number 3, checking the normal approximation. To use the normal approximation to the binomial distribution, we have to check that the normal probability, so 60 times 0.80 equals 48, which we know is our mean, and then N times 1 minus P is 60 times the 20, because remember, if we see up here, that's where we got that number, equals 12. And we can see both values are greater than or equal to 10, so the a normal probability is appropriate. For question number 4, the probability of making at least 50 shots using the normal probability. So we have our data, which we found in the previous problems, and we're going to apply a continuity correction, which is going to be this formula right here, where y is normal, and we will get this interval. So we need to calculate the z-score. So z is equal to 49.5 minus 48, that mean, and then divided by that standard deviation, which is 0.48. And when we use the normal tables, a t-table, I don't know why that was next, we can get, if we subtract that by 1, we get 0.3156. So in conclusion, this probability she makes at least 50 shots is approximately 31.56%. And lastly, question number 5, reflection. Why use the normal approximation for this problem? It's going to simplify calculations, especially for larger sample sizes. And also it's hard to compute by hand, so this is just a verified method that's been used for a long time. Problem number 2. A population has a mean of 60 and a standard deviation of 12, and a sample size of n equals 36 are taken. So first we're going to find the mean and this standard deviation of distribution. So this is going to be our plug-in, and then for the standard deviation, you're always going to use this formula right here. And so standard deviation is 2, and 60 is the mean. We already know that from up there. but this is the distribution, so don't forget that. It's the sample size. So now we're going to find the probability of sample mean, which is greater than 63. So we're going to also find the z-score again, so 63 minus 60 divided by 2, 3 over 2 is 1.5. And then again, we're going to use that standard normal table, which is the t-table. And we will finish up, and after we times it by 100, we will get this number right here. All right. So this one right here is basically just sketching the normal curve of our problem. If you can see in this shaded area, that is going to be the probability that x is greater than 63. We can see right here. And then the sample mean, where 63 and the z-score is 1.5, is going to be right here. We can see that's highlighted. So we are just highlighting the data on our table. And obviously the mean is 60, so that's where you're going to see the graph is split in half. All right, question number 4 of problem number 2. The central limit theorem, or also known as the CLT. It states, regardless of the population distribution, the sampling distribution of the sample mean, which is this, will approach a normal distribution as the sample size n becomes large. Since n is equal to 63 is reasonably large, the CLT allows us to use the normal model for the mean, even if the original population is skewed or non-normal. And lastly, increasing sample size to n equals 100, you are going to need to find a new standard deviation, which is this formula again that we just used in the past one, which we get 1.2. And then the practical meaning applied for this is the sample mean becomes more precise, there's less variability in the sample means, and estimates of population mean are more reliable. So basically, you're taking your approximation and you are simplifying it to get it more based on the actual answer. All right, and lastly for this problem is question number 6. The law of large number, and it states as the sample size of n increases, make sure no on increases, the sample mean tends to get closer to the population mean. So we're looking at a straight line. So we can take from this that n, as it approaches infinity, the mean is going to approach, the standard deviation is going to approach the mean. In this case, larger samples will yield sample means that are increasingly close to 60. So, problem number 3. A random sample of 50 students have an average GPA of 3.5. Assume that the population standard deviation is 0.40. Question number 1. Constructing a 95% confidence interval. So this is always going to be our formula for standard evaluation, I think I'm right, but yeah, for standard evaluation. So it's going to be the standard deviation over that interval, which we know, here's our standard deviation, and 95%. So when we calculate, we're going to take this number. We are not going to stop here. We're going to go to the z-score, get on that t-table, and get this number. Now we're going to do the median evaluation, which is going to be the z-score times what we just got right here, which will get us 0.11. And then we have to construct the interval, or CI, which is just going to take the mean times the ME equals 3.15 plus or minus 0.11 from up here. And then we'll get this interval right here. All right, and question number 2, interpretation of the interval. So, 95% confident that the true population mean GPA lies between 3.09 and 3.261 from this interval right here. Sums it up. And then once again, just like our other problem, this is sketching the confidence interval, so it's not the normal distribution this time. But you can see where I've labeled the upper limit and the lower limit for those intervals that we just found. And then this is going to be the mean right through here. All right, constructing a 99% confidence interval. So we have to find our margin of error, which is the ME, obviously. I meant to say error, not evaluation, last one, which is 2.5676, which we found past because it's our z-score. And that's going to be times 0.0566, which equals roughly 0.146. And the interval is going to be the construct interval, which is 3.15 plus or minus the number we just got right here. And this is going to be our new interval on not 95 this time, but 99. Now, doubling the sample size to n equals 100. Sorry, my light's being silly. We need to find a new ME, so 95% confidence, and a new standard error, which we are just going to use the same formula that we used last time. Very straightforward. So, once we have these two numbers, we just know to multiply them together, and we get 0.0784. And then, obviously, if we're doing all this, we're going to need a new interval as well. So we're going to take that 3.15 plus or minus the number we just got here, which is going to be this new interval. And then the comparison of that is the interval is narrower than the original one. Remember, we're consolidating, we're condensing. We're getting closer to our approximation. All right, last question on this one, summary confidence level versus sample size. So, increasing confidence level, wider interval, check. Increasing sample size, narrow interval, check. Because more broad, you're going to get more specific. All right, problem number 4. A soda company claims that their cans contain, on average, 12 cans of soda. A consumer group suspects the mean is less. They take a random sample of 40 cans with a sample means of 11.92 ounces. Assume that the population SD is known to be standard deviation of 0.24 ounce. So, first question, hypothesis and test type. We need to get the null hypothesis, the alternate hypothesis, and then the test type. So we know that the standard deviation is, the mean is 12. We're rounding. We know that the alternate hypothesis of 1 is that the mean is less than 12. And then we know that this is a one-side left-tailed because the consumer group suspects the mean is less than 12. It's not just different. Pretty self-explanatory. Then for number 2, test statistic and p-value. So this is going to be our go-to formula. This is our guy. And we are going to plug that in. We're going to take all of our information. We've got it all up here ready to go. This is our hypothesis. And once we plug that in, we're going to get negative 211. And then when we add that to our z-table or t-table, which you can find online, z is equal to negative 2.11, and it is greater than p, is roughly, or probability is 0.0174. Alrighty, Number 3, conclusion at A equals 0.05 since P equals 0.017, and that means that A is greater than 0.5. We reject the null hypothesis at the significant level. There is sufficient evidence to conclude that average amount of soda cans is less than 12 ounces, obviously because of the data that we have found. All right. So once again, we have another graph. This is obviously another normal curve sketch like the first one. And we can see that the mean is 12 and the sample mean is 11.92. Sorry, I'm dyslexic. And then we've got our z-score over here, which is 1 minus 1.645, which is all highlighted with all of our data. This is our approximation. This is our hypothesis. All right, conceptual meaning of the p-value. So the p-value represents the probability of observing a sample mean as extreme as 11.92 ounces, or more extreme, assuming the true mean is 12 ounces. Remember, this is our sample. All right, problem number 5, last one. A nutritionist wants to test whether a new diet changed the average cholesterol level from the historical value NO equals 200 milligrams deciliters. A random sample of N equals 15 people on the diet has a sample mean, which is X, equals 140 milligrams / deciliters. In a sample, standard deviation as S equals 20 milligrams deciliters. Assume the population is approximately normal with no strong outlier. So, for the first one, they want us to find the null hypothesis. So, we know that the mean is going to be 200, and the average cholesterol level has not changed. We can see it right here. The alternate hypothesis, which means that the mean would not equal 200 milligrams. The diet changes the average cholesterol level. It could be higher or lower because we're saying we don't know the approximation. It's alternate. And then the test type, this is a two-sided test because we are testing for any change in increase or decrease. This is the sample. They don't have all of the data. All right, number 2, test statistic and degrees of freedom. So we're going to use the t-test formula for a sample mean. This is going to be our equation. And once we plug in all of our information from up here that we've already received, we're going to get approximately negative 1.62. And then the degrees of freedom, also known as DF, is n minus 1, which would be 15, minus 1, which is 14. Because we can see the random sample up here. So that's where we got the 15 from, if you're confused. I was for a little second too. And then number 3, critical value and decision for a two-sided test at a significance level. So we know that A is equal to 0.05 and the degrees of freedom is 14, which we found up here. So the critical t value from the AT table, which we would find on the graph, unfortunately I don't have it in front of me, is going to be 2.145 roughly. And then the decision rule rejects the HO if the absolute value of t is greater than 2.45. And then the observed t value is going to be the absolute value of 1.62, which is less than 2.14, which we failed to reject. And then for our last graph, we have a T-shaped, or actually I switched these words, a T distribution, a bell-shaped curve. And we have all of our markings highlighted here. This is going to be our parameters. We can see that this is where we've got that deviation, and then our mean is 0. And our T table shows us this over here. So number 5, confidence interval, from the formula in 95% confidence interval. So we're wondering what it is. So we're going to take the mean, we're going to take the absolute of T, and we're going to times it by S over the square root of N, which is going to be 194 plus or minus 2.45 times 20 over square root of 15, and then we will end up getting this, actually I don't think I wrote it down. Let's see. This right here, because we're going to get these two numbers. Sorry, I didn't put an equal sign. But plus or minus, we have to do 2 equations, not just one. So the interpretation, since 200 milligrams of deciliters is within this interval, it supports our decision to fail to reject. All right, and last but not least, T versus Z inference. So similarities. Both test hypotheses about population means, and both use standardized tests, statistics, and both compare observed values to critical values to make decisions. The differences are that T distribution is used when the population of the standard deviation is unknown and the sample size is small. Remember, smaller and more spread out. And then the Z distribution assumes an unknown population standard deviation or large sample size. And that's it.